here's three charges on an x-axis, and we want to figure out the force on one of them. So it tells us we have charge Q1 minus 14 nanocoulombs at one position, and charge Q2 40 nanocoulombs at another. What if we stick 50 nanocoulombs between them? We got to figure out the force on the 50 nanocoulombs. So you'll never get this one right if you don't draw it first. So let's draw this x-axis like that, and notice that the farthest to the right is at 0, so I'll put the origin over here, and 0, and there is Q, let's see, that was Q2, there, okay, and then the farthest over here was Q1, so we'll put Q1 over here at minus 1.685, there, Q1, and the one we're asked to find the force on is Q3 at minus 1.215. So you don't have to get it exactly in the right place, but it helps to have things on the right side of each other, at least. There, so there's Q3. So the question is simply, what is the force on Q3? And you do have to get the direction right, so you'll indicate positive force, or to the right will be a positive number, to the left will be a negative number. I think one reason people miss this problem is the problem suggested the use of epsilon naught as the constant. So remember, you can write the force in terms of 1 over 4 pi epsilon naught as the constant, or that's 8.85 times 10 to the minus 12. Or what we've done mostly in the class is just call this k, and then it has the more mathematically friendly version where it's just 9 times 10 to the 9 Newton meters squared per Coulomb squared when you put it in Coulomb's law. So don't bother with this, you'll just make a calculator mistake somewhere. Okay, so then we have to think about how do you find the force here on this charge due to the other two. Well, you just add up the forces. You say the force, you can write it this way, the force on 3 is equal to the force that 1 applies to 3 plus the force that 2 applies to 3. So this is what we call superposition. The forces just add. You might say, well, what about this one applies a force to that one? Yeah, but it doesn't matter. Or this one affects the field created by this one here. So don't think about that. Right? We just want the force applied to 3 by the only other charges. There's 1 and 2. Okay, so we just start writing it out here. Let's see, so this is going to be equal to, so we could set it up a little bit, the force of 1 on 3. Let's go to our Coulomb's law. We always start with a constant, 9 times 10 to the 9, times charge of 1 times the charge of the other. Remember, those are charge magnitudes, so we don't worry about the signs. Right, so the charge 1 is minus 14 nanocoulombs. I'm just going to write 14 times 10 to the minus 9. And then the charge of the other is 50 nanocoulombs times 50 times 10 to the minus 9. Now you might think that charge, the positive or negative aspect, will affect which way it goes. Remember, we have this problem that the forces are really in spherical coordinates. This is a Cartesian axis. There's no way to mathematically really do it. We assign the charge. We assign the direction of the force based on whether the force is going to be attractive or repulsive. So that's why I left the negative signs off those two. If you look at the formula in the book, it's just the magnitude. And then, let's see, this is 1. Let's see, this is 1 to 3. So now we need the separation squared. And of course, for this one, the separation, you got to do a subtraction. It's going to be, you really want to do it, this position minus 1.215 minus, and then minus 1.68. I think I'll have to 5 off 5. It's equal to 0.47. And even if you mess up the signs and you get negative 0.47, it's not going to matter. You're going to square it. Again, the sign doesn't really matter in this case. All right, and now that we're all done, and none of the signs matter, we left the signs out of here, this is going to get squared. It's going to definitely be positive. So now we got to think about which way does it go and assign the direction ourselves with a positive or a negative sign. So we look and we say Q1, this is a negative charge, and this is a positive charge. Those are opposite charges, opposites attract, according to that singer. Therefore, the force is going to be that way. The force is that way, it is negative. So we put the negative sign there. Paula Abdul. Yes, that part is negative. Now let's do F23, same process. I'm going to write plus for now, maybe it'll be negative. 9 times 10 to the 9. All right, let's see, Q2 is 40 nanocoulombs. 40 times 10 to the minus 9. Q3 is again our 50 nanocoulombs. They're both positive anyway. Doing everything in MKS units. And the difference in position, this distance is 1.215. Don't have to write it negative, we're going to square it, it doesn't really matter. If that makes you feel better. It's really the magnitude of the separation, so it shouldn't be there. So you plug those numbers in, now it's all just numbers. Oh, what's the sign? Let's look here. Q2 is positive. They're both positive. And you might say, well, if they're both positive, then the force has to be positive. No. Coulomb's law is in spherical coordinates. So if we want the force on this one due to this one, they're the same charges. Like charges repel. The force is also this way. And in our Cartesian axis we set up, we made that way positive, we made this way negative. Back when I made this the origin and made these negative positions. So therefore this one is also negative, according to Coulomb's law. All right, so then we can just work out the numbers, and now it's just plug and chug. It's basically minus 12.193 micronewtons. When you're doing these problems, if it's in nanonewtons, that's a convenient time to cancel that 10 to the 9 with that 10 to the 9. There's still, I'm sorry, that 10 to the 9 with that 10 to the negative 9. There's still another 10 to the negative 9, which makes it really small, but then these are really big, and you end up with this times 10 to the minus 6. So that's how I got micronewtons. And then the other one is minus 28.52 micronewtons. For a final answer of minus 40.7 newtons, it must be micronewtons, equals minus 40.7 micronewtons, or you could enter minus 0.000047 newtons. So that one, that's it. It's really, the equations aren't so bad. It's really just a few ideas. It's getting the K right. It's getting the separations right. What goes down here is not just its position on the axis, it's the separation between the charges, and it's knowing to put in charge magnitudes and assign the direction yourself. If you do all those, you should get it right.